Now we can ask the question for distributed source coding if it's also possible lossy. As you remember, we did this for the single source coding, for the source coding with one source producing one sequence. We consider lossy source coding. What does it mean that we will consider lossy distributed source coding? That means we permit now that the estimate of the sequence xn and the estimate of the sequence yn to be distorted version of x to the n and y to the n. And as in the single sequence case, we also want to have that the average distortion of x1 and x hat n is smaller than d1, and the expected distortion of yn and yn hat is smaller than d2. But this problem is still open. So Berger and Tang were perhaps the first who make some good inner and good outer bound for this problem, but these two bounds did not match. So the best achievable region for these four tuples R1, R2, D1, and D2 is not the same as best known outer bounds on the set of such four tuples. There are cases for special channels where the Berger-Tang bound is the same. So the inner bound is the same than the outer bound. But there are also cases where the outer bound is not tied. So if you are interested in this, you can just Google lossy distributed source coding, and you will immediately come to the Berger-Tang paper, and then Anantaram 9 years ago shows a better outer bound, and you will find all this. And there are still publications in this area for special cases. And of course, as I told you, for some special cases, this problem has been solved. So of course, one of this is where y could be modeled as being independent of x. And the other case, which we will consider now, is the Slepian-Wolf. What we had considered was the Slepian-Wolf problem, where we want to have no distortion at all. That was D1 is equal D2. Now we want to consider another model. It's also a special model of the lossy source coding case. So we consider again a single source with rate distortion and site information. So this scheme was considered and solved by Weiner and Ziff in 1976. The setting is that the single cause reproduce that we want to reproduce the output of a single source with rate distortion, and we have some site information about another sequence also output by the source. In particular, this setup is identical to Slepian-Wolf coding, except that the third party only needs to recover xn, and we want to have here some distortion. And the source sends also information about yn. And we can assume that the rate is greater than the entropy of y, because we get it without any compression here. So, but this information about yn can help to deduce information about xn. So like in Slepian-Wolf, the Weiner-Ziff coding schemes relies on random generation of codes. But you will also will learn some new special trick in this case. Let's look at the graph for this. So that means let's look at length 3, small n is equal to 3. So the source outputs x1, y1, x2, y2, x3, y3. Then you see that here is the channel. So this here is encoded in some W1, in some indices, and sent to the decoder. So the decoder receives W1, which is a compression of x1, x2, x3, and y to the 3, which is exactly the sequence y1, y2, y3. And depending on w1 and y to the 3, you have to give some estimate x hat of 1, x hat of 2, and x hat of 3. And this problem had practical importance of some perhaps unexpected problems. So we can consider, for example, a wireless relay channel with a transmitter, relay and destination. And the relay might decide to pass to the destination its noisy observation yn of the signal xn. And the destination would then naturally view yn as site information. And there are many other problems where site information plays an important role.